The proper assessment of the building's performance is pivotal in order to provide serious and reliable advice to designers, architects, buildings owners, and policymakers on the real consumption of the buildings. In such a respect, dynamic energy simulation tools must be introduced. Although building dynamic simulation tools are commonly recognized as a suitable way for accurately assessing the performance of buildings, in general, more or less large discrepancy between simulated and real features can still be observed, both for new or existing buildings. Moreover, the actual gap observed in many cases seems too wide to be acceptable. In fact, measured energy use can be as much as 2.5 times the predicted one. In fact, the correct use of tools alone is not enough. The user, analyst, modeler of tools also needs to have the proper knowledge and sensibility to apply them in the right manner. Thus, some preliminary guidelines on the proper use of dynamic simulation tools and their main limitation are provided in this lesson. The main steps to develop simulation model are drawing of the geometry of building in the virtual platform, description of thermophysical properties of the building envelope, such as thickness of the walls, conductivity, density, specific heat, emissivity, and also the optical properties of glazed component, setting up the operational schedule of the building in terms of internal gains, ventilation patterns, human behavior, and HVAC system set point, and finally definition of the outdoor climate data relative to the study location. First of all, according to the features and complexity of the buildings, several simplifications have to be introduced. These represent uncertainties to take into account in the interpretation of the results. Some elements of the architectural language, such as basement, columns, frame, portals, and cornices, can be often overlooked to reduce the computation time. However, the user must be aware that the excess of simplification can be unintentionally lead to underestimate thermal bridging effect, whose magnitude may not be negligible. Once the geometrical model is ready, the description of the properties of the building envelope, which include all the thermophysical features of the technological components, is required. In this regard, the knowledge of the technical and constructive solutions adopted, such as the thickness of the wall, the roof, ceiling, and floor typology, and all the elements which allow to describe the stratigraphy of the building's components, are pivotal to obtain reliable results. The main thermophysical information to collect are: for opaque envelope, conductivity, density, and specific heat, while for transparent envelope, thermal transmittance and transmission in the solar and visible spectrum. The collection of this data can be often difficult, and several assumptions must be made, especially in existing buildings. After the envelope characterization, the operation of thermal zones related to the building's function, the user behaviors, and HVAC must be set. More in detail, the occupancy and ventilation flow rate, the lighting and appliances use, and temperature set point should be described as better as possible along the year. Due to the variety of parameters, the better way to gather such information is to record it in situ with interviews and questionnaires submitted to the occupants, or to assume reference values from standards. For example, in Italy, the standard UNI 11300 provides reference values for different types of buildings. One of the major difficulties in the simulation is the possibility to identify a reliable input value for the infiltration rate. Infiltration rate has been consequently ranked as one of the key variables affecting the accuracy of simulation results. Infiltration, in fact, is defined as the unintentional or accidental introduction of outdoor air into a building through gaps in the building envelope, often located in the frames and fittings of doors and windows. In building energy simulation software, the infiltration rate is generally applied through the parameter ACH, air change rate per hour, with a constant or variable value, ranging from 0.2 to 2 according to the type of construction. Finally, the hourly weather data related to the building site must be selected. In such respect, several databases provide an historical set of data gathered in a file easy to upload in Simulation Tool. However, in order to carry out a detailed assessment, the historical data cannot be considered any longer reliable due to climate change. In such respect, a tailored weather file can be set up based on the updated measurements provided by the closest weather station. Finally, since some errors can also be made due to the numerical model that may not adequately capture certain physical phenomena, the energy expert should consider also the following issues in the results analysis. First, the thermophysical properties of the materials are time independent, so phenomena like degradation along the time is not considered. Second, the various surfaces of the room or zone elements are isothermal, so the walls are considered homogeneous. Third, the heat conduction through the room or zone's elements is assumed to be one-dimensional. Thus, thermal bridges cannot be considered in the overall simulation. Fourth, the air temperature is uniform throughout the room or zone. Thus, the air stratification are not taken into account. In conclusion, dynamic energy simulations must be considered pivotal tools for the energy manager. They allow to estimate the real performance of the buildings and to assess the effectiveness of different interventions, also in terms of cost. Such information can be adopted also to plan and to schedule maintenance programs as well as to reduce the risk for owners and investors, for example in terms of damage and structural problems.